Hello, students. Welcome to today's intriguing lesson where we will dive into a fundamental concept of probability, understanding how sample spaces work and how we can use them to describe probabilities. Sample spaces help us generalize beyond our individual observations and allow us to analyze and agree on the likelihood of various outcomes. The plan for today's lesson is as follows. We will start by discussing what a sample space is and how it encompasses all possible outcomes of an experiment. We'll also introduce the concept of an event as a subset of the sample space. This foundation will help us organize and simplify our approach to probability problems. Through a thought experiment involving a coin and a die, we'll explore why observed frequencies can differ and how we can use sample spaces to determine true probabilities. You'll see how different outcomes can be understood and compared if the experiment conditions are equally likely. We will then introduce the notation used for sample spaces and events, culminating in a fundamental formula for calculating probabilities. This will all be tied back to our thought experiments, reinforcing the practical application of this notation to solve disagreements about probabilities. By the end of this lesson, you will be well equipped to describe probabilities using sample spaces and events, allowing you to handle a wide array of probability problems with confidence. So let's get started and delve into the world of sample spaces and probabilities. Let's start with some definitions. A sample space, usually denoted by the letter S, is a set that contains all possible outcomes of a particular experiment or random trial. For example, if you flip a coin, the sample space S is the set of heads and tails. If you roll a six-sided die, the sample space is 1, 2, 3, 4, 5, and 6. An event is any subset of the sample space. For instance, if you roll a die and want to know the probability of rolling an even number, the event E would be E equals 2, 4, 6. To see the motivation behind our need for notation, let's consider a simple thought experiment involving a coin and a die. Suppose you flip a coin and roll a die simultaneously. The sample space for this combined experiment can be represented as pairs of outcomes. Here are all the possible outcomes for this experiment. This notation helps us understand and visualize every possible outcome of the combined experiment. If we want to determine the probability of an event, such as rolling an odd number and getting heads, we can easily see that the relevant outcomes are heads 1, heads 3, and heads 5. When we talk about probabilities, we use the following notation. PE is the probability of event E occurring. E, written like this, is the number of outcomes for event E. S, written like this, is the total number of possible outcomes in the sample space. The fundamental formula for calculating probability is PE equals the number of outcomes for event E, divided by the total number of possible outcomes in the sample space. It is worth noting that this formula is only true when every outcome is equally likely. However, in this course, that is the only situation we need to know about. Let's apply this formula to our thought experiment. The event E, where a coin lands on heads and the die shows an odd number, has 3 favorable outcomes. Therefore, E equals 3. The total number of outcomes in the sample space is S equals 12, as flipping a coin has 2 possible outcomes and rolling a die has 6. So the probability of E is PE equals E over S, which equals 3 over 12, and gives a final probability of 1 over 4. By understanding sample spaces and events, we can systematically determine the likelihood of various outcomes. This approach helps us generalize and agree on probabilities based on equally likely conditions, making our analyses precise and consistent. With this understanding, you are now equipped to describe probabilities using sample spaces and events. Let's move on to some practice problems to reinforce what we've learned. We'll start with a simple problem involving rolling a die. Suppose we want to find the probability of rolling a number greater than 4. First, identify the sample space S for rolling a 6-sided die. This gives us S equals 1, 2, 3, 4, 5, 6. Next, determine the event E, which is rolling a number greater than 4. The numbers greater than 4 are 5 and 6, which gives us E equals 5, 6. Now count the number of outcomes in event E, which gives us E equals 2. The total number of possible outcomes in the sample space S is 6, which gives us S equals 6. Using the probability formula P equals event outcomes over total outcomes, we can calculate PE equals 2 over 6, which gives a final probability of 1 over 3. So the probability of rolling a number greater than 4 is 1 over 3. Now let's consider a problem involving flipping 2 coins and finding the probability of getting exactly 1 head. First, identify the sample space S for flipping 2 coins. Each coin can land on either heads or tails, so the sample space is S equals heads, 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 tails, tails, heads, and tails, tails. Next, determine the event E, which is getting exactly 1 head. The outcomes with exactly 1 head are E equals heads, tails, and tails, heads. Now, count the number of outcomes in event E, which is 2. The total number of possible outcomes in the sample space S is 4. Using the probability formula PE equals event outcomes over total outcomes, we can calculate the probability of E equals 2 over 4, which simplifies to 1 over 2. So the probability of getting exactly 1 head when flipping 2 coins is 1 over 2. Finally, let's tackle a more complex problem involving picking a card from a standard deck of 52 cards. We want to find the probability of picking a red card that is also a face card, such as a jack, queen, or king. First, identify the sample space S for picking 1 card from a deck of 52 cards, which gives us S equals 52 possible cards. Next, determine the event E, which is picking a red face card. There are 2 colors, red and black, and each color has 3 face cards, jack, queen, and king, in 2 suits, hearts and diamonds. Therefore, the red face cards are the jack of hearts, the queen of hearts, the king of hearts, the jack of diamonds, the queen of diamonds, and the king of diamonds. Now count the number of outcomes in event E, which is 6. The total number of possible outcomes in the sample space S is 52. Using the probability formula PE equals event outcomes over total outcomes, we can calculate that the probability of event E equals 6 over 52, which gives a total of 3 over 26. So the probability of picking a red face card from a standard deck of 52 cards is 3 over 26. With these walkthroughs, we've practiced calculating probabilities using sample spaces and events in various scenarios. Keep practicing these methods to strengthen your understanding. In today's lesson, we delved into the concept of sample spaces and how they are fundamental in describing probabilities. We began by defining a sample space as the set of all possible outcomes of an experiment, and an event as any subset of that sample space. Using examples such as flipping a coin or rolling a die, we illustrated how sample spaces and events are formed. We then explored a combined experiment involving both flipping a coin and rolling a die simultaneously, showing how to represent the sample space using pairs of outcomes. This helped us visualize all possible outcomes and understand how to determine the probability of specific events. We introduced the notation for probabilities where PE is the probability of event E occurring. E between vertical lines is the number of outcomes for event E, and S between vertical lines is the total number of possible outcomes in the sample space. We applied the fundamental probability formula PE equals event outcomes over total possible outcomes to calculate the likelihood of various outcomes, such as the probability of rolling an odd number and getting heads in our thought experiment. By understanding and utilizing sample spaces and events, we can systematically and precisely determine probabilities, ensuring our analyses are consistent and accurate. This foundational knowledge equips us with language to describe and generalize probabilities in various contexts,